Welcome back to Gradient Daily. Today, we are looking at the mathematics required to achieve complete, unconstrained 4D reconstruction from a single moving camera. The methodology we are examining is detailed in the ICCV 2025 paper Shape of Motion, authored by researchers Qianqian Wang, Engji Tanazawa, and Zenki Li from UC Berkeley and Google DeepMind. Capturing dynamic 3D environments over time through 4D is currently an expensive process. Industries like visual effects, AR/VR, and autonomous driving rely on synchronized multi-camera rigs to triangulate depth and motion simultaneously. Trying to extract that same 4D data from a single camera introduces a severe mathematical paradox. When you only have a single lens moving through space, the system cannot easily differentiate between the camera's motion and the independent motion of the objects inside the frame. Because of the loss of depth, an infinite number of 3D motion configurations can project to the exact same 2D pixel trajectory on your camera's sensor. You can think of this dimensionality loss like watching a shadow puppet on a wall. If the shadow suddenly grows larger, the raw visual data alone does not tell you why. The hand could be opening, it could be moving closer to the light, or the light source itself could be moving backward. Without external structural constraints, monocular dynamic tracking is an unsolvable equation with too many variables. To reconstruct these scenes, we have to reduce the math down to something a network can actually solve. Previous solutions attempted to bypass this issue by relying on static neural radiance fields, or by forcing the scene to map to predefined object templates. These methods break down when applied to casual, wild video containing unpredictable movement. Shape of Motion succeeds by applying a single governing axiom. All dynamic scene motion possesses a low-dimensional structure that can be factored. The researchers achieve this by representing motion through the Special Euclidean Group, or SE3. This mathematical group represents rigid 3D transformations, specifically pure rotations and pure translations in space, without any scaling or shearing. It operates similarly to the skeletal rigging in a 3D video game. A character's outer mesh might stretch and deform fluidly, but that fluid movement is entirely dictated by the rigid, invisible bones beneath the surface. The breakthrough of this paper is discovering these rigid SE3 bases dynamically, directly from the pixel data, without needing a pre-existing skeleton or an object template. The network performs a soft decomposition, parsing the scene into multiple clusters of points moving rigidly together. For fluid areas between these clusters, it calculates a single point's motion by blending surrounding rigid groups, expressing its trajectory as a linear combination. By forcing every pixel's motion to conform to this equation, the system drastically reduces the number of variables the neural network has to optimize. It no longer has to track a million independent trajectories. It only has to find the weights, mapping them to a few rigid bases. Factorizing chaotic fluid motion into predictable mathematical weights effectively bridges the gap between static 3D geometry and continuous 4D motion. The SE3 bases provide the necessary mathematical structure. The next challenge is accurately anchoring that abstract structure in physical space and time. The authors approach this like sculpting a 4D environment, utilizing a combination of clay and wireframe to define the shape. The clay in this pipeline is derived from off-the-shelf monocular depth estimation models. These provide an immediate frame-by-frame estimate of the spatial geometry. The wireframe consists of long-range 2D point tracks. These track specific moving pixels across multiple frames to enforce temporal consistency over the length of the video. However, these off-the-shelf priors present a problem. They are notoriously noisy. Because they are generated independently, the depth maps and the 2D tracks often contradict each other mathematically. The primary optimization challenge is resolving these contradictions and forcing these conflicting signals into a single, unified truth. The researchers designed specific loss functions to consolidate these signals, pulling the depth and tracking data together during training. Here, the SE3 basis constraint acts as the final arbiter. The network rejects tracking data that violates rigid physical geometry, smoothing over the noise by forcing the points to adhere to the basis trajectories. The innovation lies in the mathematical framework that forces noisy 2D data to conform to a globally consistent 4D physics model, regardless of the quality of the initial priors. The true power of the system comes from this ability to distill a clean, rigid truth from a collection of imperfect, noisy observations. Moving from theoretical mathematics to execution, let's examine the specific neural architecture built for the paper. Initially, the raw monocular video is split to extract depth maps and point tracks before reaching the motion basis network. To maintain efficiency, a segmentation node isolates the static background from dynamically moving foreground objects, optimizing them separately. This model was trained and evaluated on rigorous dynamic scene datasets, including NVIDIA Dynamic Scenes and the Davis dataset, which feature complex, unscripted motion. During inference, the computational load goes towards querying the optimized SE3 bases and rendering the final novel views, producing highly accurate temporal sequences. This pipeline proves that a single, uncalibrated 2D video feed contains enough implicit structural data to optimize a complete 4D network from scratch. The practical result of this pipeline is a system capable of state-of-the-art novel view synthesis for dynamic scenes. This bar chart displays shape of motion's performance metrics compared against prior state-of-the-art quasi-static NeRF models. The data shows a clear and significant margin of victory across standard image quality metrics like PSNR and LPIPS. Beyond image quality, the paper demonstrates massive performance gains in the accuracy of long-range 3D and 2D motion estimation over time. However, an academic reading of the methodology reveals specific assumptions and limitations. The primary weakness is the system's reliance on the base accuracy of the off-the-shelf 2D trackers. If heavy occlusion causes the trackers to fail entirely, the network lacks the temporal wireframe needed to prevent the reconstruction from breaking. Future work will likely focus on reducing reliance on trackers, adapting for real-time robotics, or optimizing for hour-long video. Reconstructing 4D from a single lens requires moving beyond unconstrained pixel tracking and toward a compact set of SE3 bases. This shift allows fluid, non-rigid motion to be represented mathematically as a weighted combination of those rigid foundations. By fusing noisy monocular depth and 2D tracks through these rigid loss functions, the system produces a world that is globally and physically consistent. If you found this breakdown valuable, click subscribe and leave a like. We will see you in the next paper review here on Gradient Daily.